Alrighty, so the first thing that you'll ask me to cover was how to use the d-test to classify some critical points of a function. So I've got an old final exam, and I'm going to go through the problem that's listed on there for classifying critical points. So let me grab some chalk. Alrighty, write out the problem real quick. We have f of x and y is 2y cubed minus 6xy minus x squared. And this problem already tells us what the critical points are. It says that the points 0, 0 and 9, negative 3 are the critical points. Cool. And so what we're trying to figure out is if these are minima, maxima, or saddle points. So over here, I'll write out my criterion for it. We have if the d operator is less than 0, that's a saddle point. If the d operator is greater than 0, and the second partial of x is greater than 0, that's a minimum. And if the d operator is greater than 0, but the second partial with respect to x is less than 0, that is a max. Again, the way that I remember it is that d negative is always saddle point. D positive, we then look at the concavity on x. Remember that in our usual case, if the concavity is negative, then it's a maximum, versus if the concavity is positive, it's a minimum, right? Points up from the bottom of the cup, so it's a minimum. Points down from the top of the cup, so it's a maximum. Cool, cool. We also want to remember how to construct our D operator. Remember that D evaluated at our point is, and I'll write this succinctly, fxx times fyy minus fxy squared, all evaluated at our point. So this right here doesn't mean multiplied by our point. I didn't want to write the xy evaluated everywhere, but it's the second partial of x at this point times the second partial of y at this point minus the partial of xy squared at this point. I should clarify that this squared is here. Cool. So just the partial with x and y is squared. Cool. We don't have these partials yet, so we have to find them. So the first partial with respect to x, this has no x terms. This does, so we'd move the x over. We have minus 6y. The derivative of x is 1, so we just get minus 6y. And then the derivative of x squared is 2x. And the partial with respect to y, let's see, this gives us 6y squared. This, we pull out the minus 6x. And this has nothing to do with y. Cool. Then this one, we take the partial with respect to x to get fxx. And that gives us just minus 2. Because this goes to 0, the derivative of negative 2x is negative 2. These both give me fxy. So the partial of this with respect to y is negative 6. The partial of this with respect to x is negative 6. And then the partial with respect to y twice, partial of this with respect to y is 6. So conveniently here, none of our second partials involve x or y. So we don't have to worry about evaluating there. We can just go straight into the problem. Cool. So D at our point is fxx times fyy minus fxy squared. Fxx is negative 2. Fyy is 6. And then fxy is negative 6, and we square that. Right? Fxx fx or fyy, and then fxy squared. That gives us negative 2 times 6 is negative 12 minus negative 6 squared is 36. And then this gives us negative 48, which is less than 0. Recall that our D test said that if D was less than 0, we have a saddle point. So that means that 0, 0 is a saddle point. Cool. Also, since there is no x and y in our D test evaluation, right? So there's no x or y in D. That means that this is also a saddle point, or that every critical point is a saddle point. Cool. So we also get that 9, negative 3 is a saddle point. Cool. All right. That's really all I have on this problem. Note that this problem is kind of particular in that both of these points gave the same result. They both gave saddle point, but that's only because the D operator, the D test, had no x's or y's in here. If there was an x or a y in here, then we would have different results, but it doesn't. All right, that's all I have.